And I did not forget your assignment. I decided to delay it until we take some stuff today, and then it will be posted, inshallah, this week. This is something that we discussed at the beginning, so I'm not really going to go over this a lot, except for an important part that I need to go over. And I've also organized the material a little bit in slides, which are borrowed from a book author, but they have nice organization to them, so they cover more or less what we want to cover. So remember that we talked about modeling and so on, so these slides are covering that part, how to move from a physical model to some mathematical model, and then the challenges of numerical solution to particular mathematical models. So I'm not gonna also go over these. This nice visual part, I don't know if you can see it, it's very small, but this nice visual part shows you the main numerical methods that we will discuss. We will discuss actually a little bit more than those. The basic ones, you probably covered them in earlier courses in numerical methods, like finding the roots, right? Then here, we started with the linear model, so the set of linear equations and how to solve them. We are not gonna cover curve fitting because you probably covered that already before. We are going to talk more about integration and differentiation methods, differential equations. We will go beyond the ordinary differential equations to partial differential equations, and we'll discuss also optimization. So these are more or less the big area topics. We might also cover some machine learning aspects towards the end. It's part of performing numerical solutions. I told you also that there is a MATLAB fundamentals and MATLAB programming tutorial. Again, I gave like quick, like over the fly discussion on that. Today I'm going to cover a little bit on the slides, which is gonna be good for you because I want you today also to, while we go through the part where we discuss the numerical methods, I want you also to do some programming. So I hope you got your laptops or whatever. I mentioned that last time. I don't know, I mentioned it in the class. So I hope you have your laptop. It's gonna be a good practice for you, getting used to using your MATLAB and maybe refreshing your memory if you have been using it before, or getting into speed and practice if it's your first time to go through MATLAB. Sorry, I have to take the glasses and put them in. I'm getting old, so seeing far requires me to take off the glasses. Seeing near requires me to put on the glasses. So anyways, the MATLAB environment, once you finish the installation of MATLAB, if you haven't installed it before, so once you finish the installation and you start running the program, if everything is okay, you will get like a screen full of things. It doesn't matter. The important thing is you will have a prompt in the middle where you can actually type command lines. So it's kind of it's like a text window that you can open in your Windows DOS window or whatever Windows command line, or if you use Mac OS as well, you can have a command window, right? So MATLAB also shows as a command window, and then some other things that shows you what are the variables stored in your memory, different vectors, and you can click on them, see what's inside them, and so on, and some other window which is the history and so on. That's the user interface is not a big deal. It's quite intuitive, but the important thing is that if you go there, you can just in that command line you can type something, and these things might be something like this command, so just addition, subtraction, or just regular arithmetic operations. And as soon as you finish and type enter, MATLAB is going to show you the result, and the result is always allocated to something called answer. So that's a temporary variable that stores the results of the last operation if the last operation should produce some numeric results. So MATLAB can be used as a calculator, basically, right? You can do what, yes?
Yeah, I tried 55 minus in Word 16. It gives me error.
Yeah. It just use the minus sign. It's just written here this way in a strange way. Just use the 55 and the minus sign 16. It works fine with you, right?
Yeah, it
Yeah.
works.
Okay. Variables in MATLAB, you can define variables and store values to them. So for example, a equals 4. This means that, again, the answer here is the same thing as you did, right? A, which has a value of 4. But if you have the variables window to the left side or to the right side, depending on your layout, you will see a variable called A there, and if you click on it, you can see the value 4 stored in that variable, and that variable stays with you as long as you didn't clear the variables of MATLAB. There's a command called clear, and then you can clear a particular variable by name or clear all. So you can clear all variables stored in MATLAB. I think I'm doing fine without the, okay. Now, if you don't want MATLAB to show you the result of every single step that you do, then you follow your step with a semicolon. So if you say A equals 4, and you put a semicolon, if you say this, like on the command line, you say A equals 4, and then you put a semicolon, you will not get the answer part or the answer prompt for your step, okay? MATLAB deals with scalar variables, which is like a single value variable, right? And you can define the number of bits allocated to that based on the type of the variable. So short, long, I think this is 2 bytes, this is 4 bytes. It can go up to 8 bytes as well. And then you can also define formatting. So when you say engineering, it's gonna show you things in 10 to the power 5, 10 to the power 6, 3.7 times 10 to the power 2, and so on. If you stay with the standard, it stays with the standard. Here are some examples. I'm not gonna go through them, but you can try them. The slides are gonna be for you on Blackboard, so you can try them as much as you want. In addition to scalars, MATLAB also deals in a nice way, in a seamless way, with vectors and matrices. So again, you can just create a vector or a matrix. You can multiply, divide, subtract, add, raise to the power, whatever you like to do. Whether you want to do this in a matrix operation or something else called an element by element operation. And I will come quickly to that. So for example, you can define here 2 vectors, vector A, which is composed of 1, 2, 3, up to 5. Another vector B, but when you put the semicolons this way, the vector becomes a column vector, while the upper one is a row vector. Now you can multiply a row vector with a column vector, right? If the size matches, right? And if you say A times B, you will get actually the result of the vector multiplication of the row vector A multiplied by column vector B. Here we are defining a matrix. So this is the first row, this is the second row, this is the third row. So semicolon moves you always to the next row, okay? So this is how you define, and you can also transpose this by using the apostrophe, it's mentioned here. So if you say B transpose, it's actually doing 2 operations at the same time, but since we are dealing with real numbers, one of the operations we don't see it. It does not affect. But the apostrophe is doing a Hermitian. Hermitian means that it transposes the matrix, and if the values there are complex, you get the conjugate of every single value, right? If you don't want the conjugation to happen, you say dot apostrophe. So this is gonna take a transpose without taking the conjugate of the values. You can actually access any element of an array. For example, here, if we have this matrix C, and then you say C of 2, this means that this is gonna be which element?
Second row. C2 is 4.
I think, so try this, because I think what's mentioned here is not very correct. Can you try this? So just fill a matrix with these values, or any other values, a 4x4 matrix, or even a 2x2 matrix, and then say C of 2 only. It should report the whole vector, right? Here it's showing as if it's reporting a single value. Let's see. Single value? Okay, so it's right. That's a surprise to me. Okay, so it seems that I don't know exactly how it picks that single value, but it seems to me like it's going to just taking the first. So it's only dealing with the first column, and whatever you write here is going to be the row within that column. That's new to me. I haven't tried this before. Okay, and it says here if you say C13, it would report an error because index is out of bound, right? There is no 13th element in this first column. Okay, you can be more precise and then index the elements with the row number and the column number, right? So C of 2 and 1 means you go to 2, and then you pick the first column, so that becomes the value 3. C of 3 and 2 means you go to row number 3, and then you move to element number 2 in terms of columns, and that's going to be the 0, and so on, right? That's how you address elements. You can create certain types of standard matrices, such as a matrix of all zeros, a matrix of all ones, using the ones and the zeros command. Colon operator allows you to get vectors out of the matrix, right? So for example, if that's when we deal with matrix, but here, the colon operator here allows you to create a vector. The first value specifies the start value, then the step, and then the end value. So this means that you start with value 1, the next value is going to be 1 plus 0.6, the next one is going to be 1 plus 0.6 plus 0.6, so and so on until you never exceed the end value. So it stops here at 2.8. Because if it goes with 0.6 more, it will exceed 3. So that's a vector created using the colon operator. We also use the colon operator to retrieve a vector from the matrix. Now this shows different examples of using the colon operator. I wanted to, okay, it's not written here, but I wanted to show you, for example, if we go to that matrix C, which was 1, 2, 3, 4, 5, 6, 7, 8, 9, for example, and I say C of 1, and then like this means that I'm taking the first row, right, and then all the columns across that row. So it's going to give me a vector of the first row. Okay, so the column here means span the other dimension until the end. The other way around, so C of colon and 1 is going to take all the rows of the first column. So I specified the first column, and it will give me all the values. So this one is going to give 1, 2, 3. Okay? Sorry? Vector, as a vector, yeah. Okay? And the other one, if I say C of colon and 1, is going to give me 1, 4, 7 as a column vector. Okay? So that's the colon operator when used for indexing inside a matrix. There are many other ways to create matrices with, or vectors even with a certain sequence of numbers. Something called the equal space and the log space and all these things. Just it means they are equally spaced, whether in the log scale or in a regular scale, so that you can create a matrix of sequence of numbers if you want. Also dealing with characters and strings, which is strings are basically a matrix or an array of characters. Okay, so it's an array of characters. That's also something that you can do in MATLAB. Some of the useful functions, for example, this one, very commonly used, allows you to know the length of a particular vector or the size of a particular matrix as well. When you say upper or lower, it gets you the upper value or the lower value, the max, the min. All these things are quite useful commands. Of course, I cannot list all of them or go through them one by one, but here are also some operations. So the exponentiation, I think, again, I think this is switched out, right? Yes. This should be, I don't know what this is, should be 4 times 2. But exponentiation and 4 to the power 2 is given 8 is strange to me. I don't think it's correct. Okay? Negation gives you the negative, again, minus 8 equals minus 8. Okay. The multiplication and division, of course. Left division is used to reverse the operation. So when you say 6 left division 2, it's as if you are dividing 2 over 6. Okay? While the typical one is the right division, which is, for example, 6 over 2. It's going to be, the result is going to be 3. Okay? Also, the left division is quite important in matrices because it has a special meaning. We'll see it as part of today's lecture as well. Order of operations, you have to keep that in mind. Otherwise, if you want to control the order, you will use the parentheses, similar to what you studied already in your typical mathematics. Complex numbers, as I said last time, or the time before even, that the J and the I are reserved for the imaginary numbers, so avoid using those as much as possible so that you don't spoil your complex operations over MATLAB. That's one thing. So remember I said that you can do, for example, a vector, right? 1, 2, 3, multiplied by a column vector, 1, 2, 3, right? And then if you say multiply, so if you say this is A and this is B, and you say A times B, it's going to perform the regular vector operation. Okay. On the other side, if you want to multiply a matrix with a matrix, right, without doing the typical matrix multiplication, which takes the first column multiplied by the first row, and then addition of the values, and then first column, second row, addition of the values, and so on, there is another operation that you can perform called element by element. For example, if I have A, B, C, D, and then if I multiply this regularly with E, F, G, H, we know how to do that, right? So typically do this multiplied by this and add the values, this multiplied by this and add the values, this with this add the values, this with this add the values, and the result is going to be also a square matrix, which is 2 by 2, right? However, if I say, instead of saying multiply, I say dot multiply, this means every element is multiplied by the corresponding element. So the result in this case is going to be A times E, and then B times F, and then C times G, and D times H. That's an element by element multiplication. Sometimes we need to do this operation in some mathematical calculations. And in typical math, it's called the chronicle product rather than the regular matrix product, okay? There are lots of built-in functions in MATLAB that you can use. They can help you in many things. One of the most important functions in MATLAB are the plotting functions, which allows you to draw graphs out of your numeric calculations. And there is like elaboration on that. Here is some example of drawing or plotting a graph of X versus or Y versus X values. So a few examples here, controlling the graph, putting a grid on, grid off, doing all these things from the MATLAB command. You can also do multiple plots at the same time. It's called subplot command, so it allows you to plot multiple figures within the same big figure. And you can also draw 3D plots in MATLAB, which are quite important and useful in some cases, okay? In addition to regular commands, there is also a programming capability, which is mainly composed of looping, conditioning commands, right? These are how you control a program. If you want to write an algorithm or a certain flow of calculations, you need those so that you can consider MATLAB as a programming language, right? Most important thing is that whenever you write a MATLAB program and you want to store that, it's stored in what's called an M file. And that M file can be either just a script, a sequence of operations that needs to be performed, or the M file can be defined as a function. And then in that case, the name of the M file has to match the name of the function, and you can call that by name and pass it some parameters. It's gonna do calculations and give you the result. So if you define a function, let's say fn, and it takes a parameter x and it returns a parameter y, for example, okay? And you define that the proper way inside MATLAB, and let's say the file is gonna be fn.m, okay? The file of this function, so that you have the function name fn, it has to be named the same as the function name. And then if you want to call this function from another MATLAB script, for example, you have a script that does some calculations and you call it calculate.m, and inside that script you have certain commands, and at some point you need to perform this operation. You need to do a calculation based on that. Let's say this function is calculating the cosine, for example, or doing a root calculation or whatever. Then you simply say fn, and you pass it some variable that you defined inside your script, let's say x or y or m or whatever, and the result of that you put it in some other variable, call it L, and then it will do the operation on M, return the value to you in L, okay? So that's the difference between a regular MATLAB script, which just includes commands one after the other, and a function which can be called in one line within a script to give you a certain result of complicated operation, okay? So script files, function files, the syntax, how to write them, subfunctions. You can also use, again, as part of programming, input-output commands, so printing things to the screen or taking input from the user, right? Prompting the user to put some input to you, or even taking input from file, storing the result into a file, or even beyond that, you can send it somewhere. And all these controls are in MATLAB, so it's like almost a full programming language. I'm gonna go quickly over this. It's just meant to be as a reference for you. I'm not really going to give like a full MATLAB tutorial. Here, relational operators are different from assignment operators, so they compare things. So when you say x equals 0, it means check if x is equal to 0 and return true or 1 if this is the case, or return 0 or false if this is not the case. Similarly, is smaller than a value, s is greater than another variable, smaller than or equal, greater than or equal, and so on. Not equal to, this is the not operator, the tilde. So this means check if this is not equal to m, right? So unit, maybe it's a variable, right? And then check if it's not equal to the character m. If this is true, which means that it is not equal, this is going to return 1 or true. And if this is equal to this, it's going to return false or 0, okay? So there's a difference between assignment operators and comparative operators. There are also some logical operators that does the logic operations and or not, right? On whatever variables. The decision operators, that's the conditioning ones. Selection, fine, just okay. Looping, we mentioned that already at the start. Yeah, another important thing in MATLAB, it's highly advisable when you write your program to avoid using loops by doing vectorization. For example, if I want to add the values 1 plus 2 plus 3 plus 4 plus 5 up to 10, there are two ways to do this, okay? The first way to do this is to say for loop, right? And you are looping over some variable that ranges from 1 up to 10, right? And then there is the end of the for, and inside that for loop, you are doing I plus, I equals, whatever. Let's call it A equals A itself plus I. And A is defined outside here initially as 0, okay? That's one way to do it, right? So then inside the loop, you take the first value of A, you add to it itself, and then the previous, and the value that comes through the loop. So you add 1 plus 2 plus 3 plus 4, and so on. This is doing this repeated operation through a loop. This is gonna be much slower from saying that you have a vector I, which is equal 1 up to 10 in the first line, and then in the second you say sum of I. Just a function that sums the elements inside the vector, right? And that's gonna give you more or less, not more or less, it's gonna give you the same result, but it's gonna be much faster because it's an operation on a vector. It doesn't loop. Loops are very slow, and MATLAB, clever coding in MATLAB is by trying to avoid loops and using vectors as much as you can, okay? So that's called vectorization of your code, and there is another example given here also in the previous slide. While loops, early termination, yeah, it just says that you can break out of certain loops if you want. Continue. Okay, so enough. I think these are the fancy stuff. Nesting and indentation. You can put conditions inside conditions and loops inside loops. Functions. Okay, so that's it for MATLAB. The slides are there. Please use them for your own reference and play with the tool if you haven't done that before. If you have done that before and you forgot, try to refresh your memory. It's a very important tool for this course. Okay, now we will talk about something which is very important that I didn't touch upon in the first introductory to the course, and that's the error. Because we said that one of the issues of numerical calculations is how accurate your result is compared to the true result that you can get if you can theoretically solve the system, right? And the difference between those two is called the error. And the idea here is, where do errors come from? What are the definitions of the different, let's call them errors, that can happen in your numeric calculations? And how can you evaluate the error? Okay, so there are two types of wrong things that can happen in your calculations. You can either have low accuracy or low precision. Okay, and the difference between accuracy and precision is quite explained, nicely explained in this statement and in these graphs. So accuracy means that you are very close to the desired answer, right? So here you are putting those dots the right way such that they are very close to where they should be. That's being accurate. And if you deviate from that, then you have less accuracy in your operation. Okay. Now precision means that how close are the values that you get when you repeat the same operation over and over again. Do you get the same value exactly or slightly very close to the previous one because you are keeping the conditions the same and you are repeating the operation? So are you getting the values very close to each other, which means that you are becoming very precise, or you just get diversified when you repeat the same operation, okay? And both of these can cause an issue with your solution. In all cases, they can cause errors, whether it comes from less accuracy or less precision, okay? And in general, the error, most of the time, we don't really care whether your error is positive or negative. We always care about the absolute value of the error, how far you are from the true result that you should get. And there is something called the relative error. The relative error is the value of the error divided by the true value that you want to reach. Okay, so there is an absolute error, which means that the difference between my current value and the true value that I want to reach. And there is something called the relative error, which can be calculated, for example, in percentages, or it's a value which should be smaller than 1, right? And in that case, you are doing the error divided by true value. Okay, so that's the relative error. Okay. Okay. Typically, while doing your calculation, you cannot really figure out what's the true value that you want to reach. Otherwise, there's no need for your numeric calculation, right? And in most of the cases, with each numeric operation, there is an estimated error value, right? Rather than an actual true error value. Okay, that estimated error value is always calculated using some formula that relies mainly on the algorithm that you are using and the parameters that you can set when you are tuning the algorithm. For example, if you are doing an iterative algorithm, there's a step from one point to the next point. How big is the step? And then typically we get the error as a function of that step. Okay? So you always have an estimate of the error. You don't really have the true value of the error, because getting the true value of the error means that you need to know what's the true solution. And if you know what's the true solution, there is no need for the numeric solution in the first place. Okay? And in most of the time, you are doing the calculations, repeating your adjustment or repeating your numeric operation until the error becomes smaller than a particular given threshold. Right? So you always have some bound on the error, and you want your estimated error to be smaller than that bound. And remember, we are always working with the absolute value of the error. So plus or minus, we deal with them the same. And that, once you reach this condition, we call that the stopping criteria. Because otherwise, you will keep on calculating and refining, even very small refinement, but you are wasting time, right? So your solution takes much longer if you keep running and you don't stop at some point. So how do you define where do you stop? By having an error threshold defined to you, which is called the stopping criteria. Okay. Two types of errors happens in numeric calculations. The round-off error, which comes from finite precision of calculation, and the truncation error, which comes from the approximations that you do in order to be able to solve numerically, right? So instead of, for example, instead of going through continuous values, you go through discrete values with a certain step. This causes a truncation or a round-off error. Truncation error, because you decide that I'm not gonna take every single value, I'm gonna just jump in values, while the round off comes from the fact that your computer, for example, uses 16 words or 16 bits to represent any integer or any floating point, right? So that has to come from the limitations of the computational device that you are using itself, okay? That's called the round off error. So again, it goes through a couple of slides talking about the representation of numbers in computers, which are represented using the binary system, zeros and ones. I think everyone is aware of that because you have heard of computers already, right? So anyone is not aware of what's the binary system, how it works inside computers and so on? No? Yes? Everyone is aware? Anyone not aware? No hands up? Okay, good. So I'm going to skip those couple of things, and the truncation error. So truncation error, for example, comes from, remember when we talked in the first or the second lecture, we talked about Taylor series representation, and we said that you don't go through all the derivatives, which means that you will have probably in many cases infinite number of terms in the Taylor series. You stop, for example, after the first derivative. And then based on that, we are not representing the smooth curve as it should be, but we are truncating at some point, and this causes some error called the truncation error. So you have two sources, precision error, truncation error. You need to account for both of them when you are doing your numeric calculation to figure out what's the total error that you are going through. Nowadays, in most of the cases, but not all the cases, the truncation error is more significant as compared to the precision, because computers of these days, they have really much better precision than like 20 or 50 or 30 years ago, right? Now we have much better precision in our calculations, but still, in some specific cases when you deal with extremely large numbers, or when you deal with extremely small numbers, or when you deal with values that are very close to each other, precision kicks in as a source of error, okay? Otherwise, in most of the other calculations, the truncation is the more critical error that you care about. Okay. So that's just the Taylor thing we talked about last time, several times before, so I'm not going to go through it. The most important thing is to know that because we are going to use the Taylor series expansion a lot in terms of our numerical calculations, specifically when we deal with differential equations and so on, the most important thing to keep in mind is that 90% of the time we will be using first order approximation for the Taylor series. So after the first derivative, we stop. This means that the overall error that we get from this system is going to be of order of square the step. H is the step that you use to move from one value to the next, okay, in the Taylor series expansion, okay? So most of the time, if we are using a first order approximation, the order of the error is going to be proportional to square the step. So the smaller the step that you have, the better the accuracy of your calculations, because you have less error, okay? And this is a truncation error, don't forget, okay? So in many cases, and actually this is one practice that you can do on, I don't know if they had it in the previous slide, probably. So the one practice that you can do is just to take, for example, the exponential function, and then just plot the exponential function using reasonably, of course, in MATLAB you cannot have a continuous value, right? You just create a vector. Why don't we do that? So open your, that's a simple exercise in MATLAB. So the first thing that you want to do is to plot, okay, the y equals e to the minus x, and the values of x belong to the range from 0, let's say, to 3. Okay? So plot this exponential function, and then after that represent this function using Taylor series with step h equals 0.5, and then try again with h equals 0.1, and then try again with h equals 0.01. Okay? And plot the Taylor series representation in all these cases. Okay? Compare that with what you have on the actual plot of the signal. Now, this actual plot of the signal, I recommend, for example, using 0.01 step here, just to plot the signal itself.
Sir, can you give us time? I open my map app. Or sorry, just look at I'm open my map app.
So you are able to open it?
Yeah.
You mentioned the step should be like 0.4.
Yes.
Still on the same slide?
Yeah.
Okay. The step is what you do for x. You did 0.4, now we use for 0.0.
So that for the Taylor series, right? You would say that y is equal, or y of y of a is equal to f of a, right? Plus h multiplied by f dash of a, right? Dash. This is the first order Taylor series expansion, right? Correct. The first order expansion. Hmm? And then plot this for a values that starts from 0 and goes with steps 0.5, 0.5, right? Steps of h. And then for h equals 0.1 and for h equals 0.01.
Every time you just have to.
Y equivalent.
Yeah, I know, but like, why do I keep?
Just consequence two functions. Finish the three of them. But it will take some more time if we reduce, let's say, the step.
Of course, because you are doing more calculations.
This thing, MATLAB is the Python is the closest language to MATLAB as a programming language.
It is, and it has more or less the same features in the basic calculations, not toolboxes and some of, even Python is growing maybe. So now you have toolboxes for geometry, you have another toolbox for control, a third toolbox for this. But most of the work done in Python is more focused on machine learning approaches. So that's where you have really more libraries compared to anything else. So anyone was able to?
Yeah, I get the three of them.
Yeah, show me. So it gets closer to the curve, right?
Yeah.
Did you plot them on the same or?
No, it should be in the same thing.
Yeah, try to plot it on the same. Okay.
All of them.
Yes, because now you can see that it gets closer to the curve, right? Anyways, I don't want to waste a lot of more time on this. But you can try the exercise even if you didn't manage to do it here. You can try it offline. I want to just finish with those set of slides. So, just important thing is in numeric calculations, there is a simple operation that we do always to perform or to represent differentiation. If we cannot really, if we have a function which is not easy to differentiate, then we can represent the differentiation in the numeric form, either by a forward or a backward or a centered, but anyways, the principle is the same. So when you want to get the first derivative of a particular function, you do the function at a point and a point before it, right? So here, you want to get the differentiation of this function at xi, you take the point after xi, so xi plus 1, you subtract from that the value of the function at xi, and then you divide by h, which is the distance between xi and xi plus 1, okay? That's the step of the numeric calculation. And again, this operation has an error, a local error of order h, okay? Or you can do backward calculations. So if you want to calculate the derivative at point xi, you use xi and the one before it, the one which is h step before that, and you still divide here. If you want to get some middle value, right, which has a better error performance, then you use what's called the center. In that case, if you want to get the derivative at a certain point, you use the one before and the one after. And then in that case, you divide by double the step, because now you have used 2 points that are 2h far from each other, right? They are shown in the diagrams here, the 3 approaches. And the nice thing about this is that it has a better error performance. The error here, if you use smaller h, then the error gets much smaller, quicker than the error of the other 2 cases, okay? I'm gonna just, okay. The important part here was to look at whenever, the whole idea here is whenever we are performing some numeric calculation, there are 2 things that you need to look at. One of them we focused on it right now, which is basically that particular algorithm. What's the error associated to it? And if it's not, but most of the algorithms, you have the error already defined for you. If you come up with your own algorithm, then in that case, you need to derive what's going to be the error of that, particularly the truncation error. Of course, also you need to account for the precision, but the precision is not algorithm dependent. It's more computational capability dependent. Okay? All the algorithms that we study will always get an associated expression for the error for that error. So here is this algorithm to address that problem, and here's an expression of the error for that algorithm in terms of the parameters of the algorithm, as I mentioned, in terms of the step size, for example, in case of Taylor series, in terms of sometimes even in terms of the number of iterations, because in many cases the error gets smaller as you do more iterations. Okay, so that's it in terms